Okay, hello everyone. In a new video, in this one we are going to solve an exercise related to mechanics in the chapters of mechanical actions and equilibrium of a body. This exercise was the previous one in the brevet exams in 2010 first session, third exercise. The title of this exercise is Equilibrium of an Iron Ball. An iron ball of center of gravity G and of mass m is equal to 500 grams. Then here the mass of the ball is given by m is equal to 500 grams. So we know that grams is not the SI unit of mass. In order to convert from grams to kilograms, we simply divide by 1000. Then 500 divided by 1000. So the mass in the SI is given by 0.5 kilograms. Is connected to the free end of a spring balance. Dynamometer of stiffness K is equal to 100 Newton per meter. Then the stiffness of the spring is given by K is equal to 100 newtons per meter. So here, what does the stiffness represent? In order to elongate or compress the spring by 1 meter, we need to apply a force worth of 100 newtons. And take G is equal to 10 newtons per kilogram. Now, number one, the ball is in equilibrium under the action of two forces. Here, although they didn't mention this figure, but here, since they mentioned the equilibrium, so they are talking about this document. So it is at equilibrium. Now we can use the condition of equilibrium. Now in part A, they are telling me that one of these two forces is the weight W of the ball, name the other force. So here, because the ball has a mass, then it will be subjected to its weight. And because we have a spring, then the other force will be the tension force. So the name of the other force is given by the tension T. Now in part B, give the line of action and the direction of the weight W and calculate its value. So here, by calculate its value, they are asking me about the magnitude of the weight vector, which is W. So let's start by specifying the line of action. And the direction. We know that always the weight acts vertically downward, so the line of action is vertical and the direction is downward. Now as for the magnitude, now here, because we have the mass and we have G, then we can calculate the magnitude via the following formula, that the weight is equal to mass times gravity. Now the value of m in the SI is given by 0.5 and the value of G in the SI is given by 10. Plugging this on the calculator, it will give me 5. Since everything in the SI, so the value of W will be in the SI, which is in newtons. So weight is equal to 5 newtons. Now in part C, write down the relation between the two forces vectors, two force vectors at equilibrium. So here they are asking me about the condition of equilibrium, which is given by. So how do we apply this condition? Always we start by writing at equilibrium. Always on the left we write the sum of forces acting on the ball, which is given by the weight and the tension T, then W vector plus tension vector, and on the other side we write the zero vector. We don't forget the vector over the zero because this is a vectorial equation. Now moving T to the right hand side, so we'll have W vector is equal to minus T vector. Now the first equation tells us that both W and weight act on the ball in order to give me the equilibrium, which is the zero vector. And the other equation tells me that both forces, the weight and the tension, have the same line of action. The minus sign corresponds for the opposite direction and same magnitude. Now in part D, they are telling me deduce the line of action, the direction, and the magnitude of the other force acting on the ball. And by deduce, it means that we need to use the previous part. So in part C, we have determine the condition of equilibrium, which is given by W vector is equal to minus T vector. And we already know that the weight, so this in part B, these are the properties of the weight. So because this equation tells us that both forces will have the same line of action, opposite direction, same magnitude, then we can directly deduce the properties of the tension T from the properties of W. So they will have the same line of action, which is vertical, opposite direction, so the weight is downward, the tension will be upward, and they will have the same magnitude, so T will be equal to W equal to 5 newtons. Then the line of action will be given by vertical, the direction is upward. As for the magnitude, we know that W vector is equal to minus T vector. Now in this case we are interested in the magnitude, so let's write in magnitude that the weight will be equal to the tension. So here we drop down the vectors and we get rid of the minus sign, but we know that the value of the weight in magnitude is given by 5 newtons. Then in this case the tension T is equal to 5 newtons. So here let me write that the weight is equal to 5 newtons, and as for the tension T, it's equal also to 5 newtons. So in part E, they are telling me to find the elongation x1 of the spring balance. And we know that the elongation can be determined from Hooke's law, because now we know the tension and we already have the stiffness as a given. Then let's say apply Hooke's law. Hooke's law is given by that the tension is equal to the stiffness of the spring multiplied by the elongation. Now here the elongation is denoted by x1 and not delta L. Since the elongation carries the index 1, so the tension will carry also the index 1. Or before putting the indices, let's construct the triangle of this formula. So here, because we have multiplied and T will be at the top, okay, and X are at the bottom, we are interested in finding the value of X. Then X, which is denoted by x1, will be the tension divided by the stiffness K. Because the elongation carries the index 1, so the tension will carry also the index 1. The value of the tension is given by 5 and the value of the stiffness is given by 100. Plugging this on the calculator, it will give me 0.05. Since both the tension and the stiffness are in the SI, so the value of x1 will be in the SI, which is meters. Then the elongation of the spring is given by 0.05 meters. Now in number 2, a magnet is now placed under the vertical line passing through G. It thus pulls the ball with the force F. The elongation of the spring balance becomes x2 is equal to 8 centimeters. So now here what we have done is that we placed a magnet along the vertical line passing through G. So this is the vertical line that is passing through G. And we have placed a magnet. So here we have two possible cases. Either we have placed the magnet here or placed the magnet here inside the spring. So, and in this case, the elongation of the spring changed from x1. So the value of x1 is given by 0.05 meters. Then the value of x1 changed from 0.05 meters to x2 is equal to 8 centimeters. So centimeters is not the SI unit of length. In order to convert from centimeter to meter, we simply divide by 100. Then 8 divided by 100. Then x2, the new elongation is given by 0.08 meters. Then the elongation changed from x1 is equal to 0.05 meters to x2 is equal to 0.08 meters. Now in part A, find in this case the value T2 of the tension and the spring balance. So, and this can be determined using Hooke's law because we know the value of x2, the new elongation, and the stiffness K of the spring will not change because this is a characteristic of the spring. Then in part A, let's say apply Hooke's law. Hooke's law is given by T is equal to K multiplied by X. So T carries the index 2 as well as X. Now the value of K is given by 100 and the value of X2 is given by 0.08. Plugging this on the calculator, it will give me 8. Since both K and X are in the SI, so the value of T will be in the SI, which is in newtons. Then the value of the tension T2 is given by 80 newtons. And now in part B, they are telling me by comparing T2 and W. So let's start by comparing T2 and W. The value of T2 is given by 80 newtons. Whereas the value of W that we have determined in number 1 part B is given by 5 newtons. So by compare, we need to say whether one is greater than the other, equal or less than. So here as we can notice that the value of T2 is greater than W. Now let's complete the question. Show that the magnet is under the ball. So here the tension T2 acts on the ball vertically upward, whereas the weight acts on the ball vertically downward. And here, because the magnitude of T2 is greater than W, so the action of T2 is greater than the action of the weight. So in order for the ball to be at equilibrium, there must be another force acting vertically downward in order to balance the effect of the tension T2, because T2 is equal to 80 newtons, whereas W is equal to 5 newtons. So in this case, let's say since T2 acts vertically upward, while W acts vertically downward, then the magnet is under the ball. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon in another one.